Hello, today I want to introduce our work AutoDA, Automated Decision-Based Iterative Adversarial Attacks. I am Qian Fu from Tsinghua University. This work tries to automatically search for good adversarial attack algorithms. These attack algorithms can generate adversarial examples to attack machine learning models. Let me first provide some background knowledge on adversarial examples. Deep neural networks have been integrated into several security-critical application systems. However, deep neural network classifiers are vulnerable to adversarial examples. Attackers could fool the classifier by imposing small adversarial perturbations onto normal images. As you can see from this figure, adding small adversarial perturbation onto normal image can fool the classifier to classify elves as dog. Adversarial examples bring potential risks to these security-critical applications. Thus, various adversarial attack and defense methods have been developed. Adversarial attacks aims to generate adversarial examples under some specified threat model, while adversarial defenses tries to defend against them. To measure the quality of an adversarial example, researchers usually use L2 or L infinity norm of the corresponding adversarial perturbation. A smaller norm means better adversarial example, since the perturbation or noise would be more imperceptible by human eyes. For example, L2 attacks would try to generate adversarial perturbations with lower L2 norm. Divided by the attacker's goal, there are targeted and untargeted threat models. Untargeted attacker aims to cause misclassification of the classifier, while targeted attacker moves one step further and aims to cause misclassification to a target class. Divided by the attacker's knowledge about the target model, there are white box and black box attacks. White box attacker knows everything about the model, including its architecture and parameters. As for black box threat model, the model is a black box, and the attacker can only query the model. For example, under the decision-based black box setting, attacker can only send images to the model and query for their final classification labels. In general, attack with less knowledge about the target model is usually more challenging and practical. As for defense methods, adversarial training is one of the strongest defenses. The basic idea is adding adversarial examples to training set. But why we need automated attacks? On one hand, developing adaptive attacks is necessary to evaluate defenses. These adaptive attacks are designed by domain expert case by case and require lots of trial and error efforts. Automated attacks can ease these burdens. On the other hand, many of existing decision-based attacks are based on heuristics. Automated attacks can serve as reasonable baselines and help us examine the rationality of these heuristics. There are two fields trying to automatically solve problems. They are program synthesis and automated machine learning. Program synthesis aims to find programs satisfying some specification or constraints. Its search space is constructed from programs. Program synthesis work usually use solvers to solve these specification or constraints. On the other side, neural architecture search is one of the most well-known directions of automated machine learning, which aims to find network architectures achieving higher accuracy. The search space is usually constructed from expert-designed network layers. Advanced search methods, including reinforcement learning and gradient-based methods, are used. In general, program synthesis problems are usually more logical, while NAS problems are usually more numerical. The problem of automatically discovering decision-based attacks lies between these two fields. In general, synthesis program with control flow is an extremely hard problem. When we studied the implementation of two existing decision-based iterative attacks, we found that they share quite similar control flow. Their main difference lies in a loop-free code segment, and this code segment uses only a dozen of mathematical operations. These observations gave us the intuition we can fix the control flow using an algorithm template and search for the loop-free code segment only. In this work, we follow the general methodology used by program synthesis and NAS. First, we define the search space consisting of programs for our problem, then design a search method to explore this search space. Finally, we define evaluation methods so that we can tell good programs from bad ones in the search space. In this work, we use the random walk framework for the L2 decision-based attacks proposed in the boundary attack and used by nearly all later decision-based attacks. The random walk process starts at an adversarial example. We can obtain this adversarial starting point easily by adding large noise to the original image. At each random walk step, the algorithm invokes the generate function, which returns next point to work to. When the next point is also an adversarial example and is closer to the original image than the best adversarial example we already found, then we update this new point as our best adversarial example. If it is not adversarial, then try again. The generate function accepts two arguments, the best adversarial example x we currently found and the original image x0. Based on the random walk framework, we can only search for the generate function. Designing search space is to trade off between expressiveness and complexity. We design a DSL for our problem. Then we define our search space as programs in this DSL. This DSL contains only 10 basic scalar and vector mathematical operations. It does not support control flow. We also design the program to accept an extra argument n. It is a standard Gaussian noise to provide randomness to the generate function. This DSL provides enough expressiveness for our problem in a sense that it can express the boundary attacks generate function. To explore this search space, we design a random search method combined with two pairing techniques and two priors. The first pairing technique is input check. We filter out programs not using all inputs. The second is distance test. The generate function needs to reduce the distance between adversarial example and original example as required by the random walk framework. We also generate programs with less unused statements and add 3 predefined statements to the program, since nearly all existing attacks would use them. As for program evaluation methods, usually we would run large-scale experiments to evaluate attacks. However, this kind of evaluation is too computational costly. Instead, we use a small and fast InfiniNet binary classifier on CIFAR10 dataset, and we only evaluate programs to attack a handful of examples to save GPU time further. As for the metrics to evaluate programs, we use the ratio of the distance between adversarial example and the original image to the distance between starting point and the original image. Lower ratio means better program. Decision-based iterative attacks need to run for numerous steps to work. To reduce computational costs, we first evaluate programs for a small number of steps and only evaluate the best program in each batch for a larger number of steps. We implemented a prototype of AutoDA from scratch. The core functionality of searching for programs is implemented in about 4,000 lines of C++. This prototype has two modules. The program generator generates programs with the two priors and filters out bad programs using the input check and distance test. The program evaluator evaluates programs against the classifier on GPU. Communications between CPU and GPU tasks are done asynchronously in large batches to achieve enough performance. We ran this prototype to search for programs. We organized this experiment as 15 runs. Each run allows 500 million queries to the classifier. More than 100 billion random programs are generated. Most of them failed in the input check and distance test. This shows the effectiveness of our pairing techniques. We plot the lowest L2 distortion ratios found in each of the 15 rounds in this figure. Since the top two programs' ratios are quite close, we select them both for further benchmark experiments. We call these two programs as AutoDA first and second. After discarding unused statements, these two programs only contain 10 and 13 statements. We are surprised that they are quite short. We benchmarked our attacks against 4 expert design decision-based attacks, including 2 strong attacks, HSJ attack and sign-opt attack. We used 2 benchmark metrics widely used by existing work, the L2 distortion versus queries curve and the attack success rate versus queries curve. In the first group of experiment, we benchmarked these attacks on 4 widely used models for CIFAR10 dataset. As you can see from the results, our attacks are much stronger than the boundary attack and the evolutionary attack. Our attacks converge faster before about 7,000 queries, while converge to slightly worse adversarial examples than sign-opt attacks afterwards. Considering our DSL is only able to express the boundary attack and not able to express the stronger HSJ attack and sign-opt attack, this is impressive. This table provides some numerical results. The AutoDA first achieved only less than 1% worse L2 distortion than the sign-opt attack at 20,000 queries. We also benchmarked our attacks against models on larger datasets and defense models, including 2 ImageNet models and 2 adversarial trained models. The results are similar to CIFAR 10. To conclude, we present AutoDA, a novel solution to automatically discover decision-based iterative adversarial attacks. We proposed a way to construct a search space for decision-based attacks and an effective search algorithm. We implemented a prototype of AutoDA and ran experiments. The discovered attacks are simple yet powerful. They show comparable performance with SOTA expert-designed attacks, suggesting these expert-designed attacks are near optimal in our search space. Thanks for listening.